Hi, in this lecture, we are going to look at the internal structure of the atom, specifically these two models, the Bohr's model, the Brouwer's model. Specifically, well, these two models are actually equivalent, but uh, uh, you find it interesting that their approach look different. And then from these models, the theoretical models of the atom, any atoms, can be explained by these simplified models. That constitute the quantum mechanics. We can understand how light interacts with the atoms, so that a photon, a particle of light, is either emitted or absorbed by an electron, residing inside the atom. Right. And one of the most prominent example or applications of this quantum mechanical structure of the atom is the lasers. I think you have all of you have heard of this name, lasers. What is lasers? How is it used? It has a variety of usage in industry, in all kinds of industries, ranging from medicine to manufacturing. So we're going to look at that. Well, when you break up a light using the diffraction grating, you can split the light in terms of the wavelength, right? Just like a prism, you let the light go through the prism, and the light exited from the prism. It's split into a rainbow color, right? So we do the similar thing on this discharged light inside the tube with the sealed gas in it, and then we apply a strong voltage across, so that the gas is energized, and energized gas releases a specific wavelength of the light for depending on what kind of gas, what the gas is made out of. If the gas is made out of sodium gas will produce this emission lines. Lines, these bands of light is unique to each kind of atom. Hydrogen has emission lines at these particular locations in the spectrum. Calcium has many other bands. It's like a fingerprint or barcode that each element carries. Each element has its own specific barcode, like spectral lines. So by splitting the light coming from an unknown star using diffraction grating, we can know what the star is made out of. Well, mostly the stars are made out of hydrogen, but yeah, there's a small amount of other elements, such as magnesium, calcium, carbon, something like that. So we can understand the contents of something that you can never touch. Well, but what sets the location of those bright bands in wavelength spectrum. Well, to understand, that has a lot to do with the atomic structure, how the atoms is structured internally, and without understanding the quantum mechanics, you cannot describe that phenomenon, right? You see, if the electrons were allowed to orbit at any radius around the nucleus, then you couldn't produce that kind of band structure. It should rather produce the continuous radiation spectrum, right? So there comes the physicist named Bohr, who first he's one of the major physicists contributed to the construction of the quantum mechanics in the early stage. Yes, his model is very important to understand how electron resides inside the atom. Well, this crude picture, can well explain. It's pretty good way to understand it. It's similar to the classical model in that electron orbits around the nucleus, but there are multiple orbits around the nucleus, but they're fixed radius. Yeah, this radius is set. This is the ground level, and that's the second level, and that's the third level, and there's more levels up outside, but you can't draw. I couldn't draw a picture, so that's why I drew only two orbits. Right. So the radiation occurs only when an electron orbiting in a certain orbit transitions down to the lower energy levels. Each orbit has different energy levels, okay? EF stands for the final energy state. EI stands for the initial energy state. Okay, right now this electron is orbiting in the initial orbit, which has a higher energy levels. Okay, it's like a apartment building. This is the second floor, and this is the first floor, because it's a ground level. Okay, so here's the important part. The electron in a high energy state right now, in the initial state, can make transition to a lower energy state, so it can come down to this smaller radius orbit by emitting a photon whose energy was the difference of these two states. You see, the potential energy of these two orbits is different. EI is greater than EF, but the energy has to be conserved, right, before and after the transition. So by falling down to the lower energy levels, this electron releases the difference of the energy between these two energy levels in the form of photons. Toward towards outside. So this is what we call the emission of a photon. Okay. So the electron doesn't. The only thing happened is that the electron has changed, jumped from higher position to lower position, and this energy, the height difference, it should be equal to the energy of the photons that is emitted. And you remember the energy of the photon is written as h times frequency, right? So we have this formula. We should have this formula, right? Okay, does that make sense? The Bohr's model is very important. So I want you to understand how it works. It's not that difficult once you understand it. Now, but why the people were very puzzled by this model? Why there is such a discrete orbits allowed? Why can't electron, stay in between those two orbits? What's prohibited? What's prohibiting the electrons to orbit in between? And then one of the explanation can be made by this model called the de Broglie model. He treated electron as a standing wave, or matter. We call it matter wave. Matter can be either treated as a wave or particle in quantum mechanics. So he explained the behavior of electrons, which normally is perceived as a particle, but he treated as a wave, like traveling along the chord. Okay, and if the this trajectory at the circumference of the radius is the multiples of the one wavelength. The r is in the lambda. Yeah. So when the wave comes back, go around and comes back to the original position, and it closes, the standing wave is formed because two ends is the node, right? If you remember the wave section. Therefore, this wave can withstand and remain oscillating in this orbit indefinitely, which means that the electron can stay, is allowed to orbit around this particular radius, while this is the in-between radius case, where this relationship doesn't follow. The circumference of this circle isn't the same as the wavelength of the matter wave. This is the electron mass. Okay, the wavelength of matter wave is written like this. Okay, and this the matter wave will destroy themselves through the destructive interference if the standing wave condition cannot be satisfied, namely this condition. If the circumference of the orbit isn't the integer multiples of the wavelength of the matter wave, then this wave that started out, the peak, doesn't after looping around one circle, it doesn't come back to the original position. right? So therefore, as the waves travel along this path, wave will start canceling by itself, and it will diminish. Right? So in this case, the wave cannot survive. While the case B is when the electron can stay. So that makes sense and that matches with the experiment. And in this way, he can explain beautifully how electrons should behave, should stay where it should stay inside the atom. So we learned that the photon is emitted when the electron orbiting around the energized orbit, higher orbit, falls down to the lower, more stable orbit. Then the excess energy between these two orbits is released in the form of photons. This is a photon, okay? That's called emission. Absorption is the reverse process of emission. Yeah, it can go the other way. Yeah, the electron can be energized by observing the energy of the absorbing the photon with the energy with the same amount as the energy difference between two states. Then this electron can jump up to the higher energy level. But as you saw, there's a restriction on the wavelength of the incoming photon, though. It has to be exact same as the energy difference between two orbits. Otherwise, this electron won't interact with the photon. The photon will just pass through the atom, and it just doesn't excite the electron. Okay, so in this way, Niels Bohr, he was a pioneer of quantum mechanics, was able to predict exactly where the spectral lines of the hydrogen atom would be. And this was the very radical departure from the conventional theory, and that led to the new paradigm in physics called quantum mechanics, and it can explain all sorts of phenomena in the atomic or subatomic scale. Yeah, without this, nothing can be explained. And then one of the interesting consequences of quantum mechanics that everything, all physical quantities in quantum mechanics has to come with the probability, unlike classical mechanics. It's not because the system is small or tiny, so you have some error in measurement. No, it's not because of that, but because mathematically it's proven that it's impossible to measure certain physical quantities such as mass and the momentum and velocity, or energy and time, or something like that, at the same time. And this is known as a Heisenberg uncertainty principle. Yeah. Right. So there's some fuzziness associated with quantum mechanics that makes lots of physicists, confused, and it's very difficult to treat mathematically. Right. Yeah, so in classical mechanics we can exactly measure the position and velocity of the particle at the same time, right? Using the yardstick and odometer or speedometer, you can measure it, but in the atomic level, your measurement itself can alter the system by itself. Because when you try to look, you apply light, right, to the target. And this motion of applying target disturb the system. So we can't know the true nature, true uh, behavior of the electron until you make a measurement. Now this is known as uncertainty principle, which essentially states that it's impossible to precisely measure position and velocity at the same time, right? Which is why electron is treated as a cloud of probability surrounding around the nucleus. That's the most correct picture in quantum mechanics. Right. The Bohr's model and de Broglie's model is like a toy model for the Heisenberg model. Heisenberg model is the most accurate model where electron is treated as a cloud of probability. But that's very difficult to fathom, right? Now the laser. Laser is the, as I said, most widely used a quantum machine or device everywhere. Laser stands for light amplification by stimulated emission of radiation. Well, it sounds kind of difficult, but basically it uses this emission of light, by bringing the electron down from the higher energy state. Right. Well, in order to do that, we have to apply electricity and raise all the low energy electron up in the high energy state. Okay, bring them up. This is called pumping, laser pumping. And then pumped up, you pump up the electrons, and that electrons, it's very easy to go down because it's unstable state, and all of them will start to come down to the lower energy state at the same time. So that creates the tightly collimated beam of light at the single wavelength. That's the laser. Right. Ordinary light that we see now it's like this, the incoherent radiation. Right. When atoms are vibrating due to the thermal oscillation, thermally, its motion is very random, right? It jiggles around in all sorts of direction, and when it jiggles, it produces electromagnetic radiation, and that's of various wavelengths and directions, right? So that's why the scattering and happens and stuff like that, right? And then light is whitish in color. It's a mixture of everything. But the laser is like a marching military infantry. Okay, all the atoms are in the same state. We set up the device so that everybody, all the soldiers, are, wearing the same uniform, same everything, and then we order them to shoot the gun at the same time, which is the photon, and everybody shoots the gun at, the same bullet, same photon, same everything at the same time. So that produces this collimated, when light is photon is shot in the same direction with the same wavelength, they strengthen each other through constructive interference, right? So the intensity of the laser beam is very amplified, becomes very strong. And the color, of course, of the light, the laser beam is unicolor, because everybody is emitting the same wavelength of light, photons. And this is achieved by bringing all the electrons in all the atoms in a higher energy state, and there is called a stimulated emission. Stimulated emission happens when you introduce the photon with the same energy difference, with the same energy difference between two bands, energy levels, and then that induces this falling of electron, transition of electron down to the lower energy state. So that results in two photons, right? As the picture shows. So this situation, well, this photon triggers the emission of other photons, other atoms too, just like a nuclear chain reaction. So this stimulated emission occurs all at once. Right. And whereas spontaneous emission occurs naturally, because the energy in the electron in the higher energy state wants to relax by releasing photon, and then go down to the ground state. And that happens sporadically, but that's not how the laser is made. Laser is made through the stimulated emission, where photon is introduced from outside. And well, the laser device, there are two types of laser device, but the first kind is the gas laser. Gas laser, this is the helium neon gas laser, where the helium neon mixture is sealed inside this tube, and a vacuum tube, and then their mirror set up on both ends, but the one of the end is half mirrored, partially mirrored. So some of the photons can escape, like 30%, 60% or something. You can change that. But the majority of photons is bounced back into the chamber. Okay, and then the photons, produced inside this chamber will travel back and left and right, back and forth, amplifying more and more photons. And this can be shown. I want to show this by this simulation. When you click this link, this allows you to download this Java file. Here I'm showing you the model of the gas laser, and this is the light source you use, and then these are the atoms, gas atoms, the helium or neon. Okay, and then let's put the mirror, and then we can change the reflectivity of the mirror, right mirror, not the left one, the right side. Yeah. Okay, then let me adjust a little bit so that the lasing will start faster. Okay, as soon as you notice that I turn on the lamp it's as striking, showering the photons. See the photons now. You see some of the atoms inside the chamber is excited. These numbers indicates the energy level. There are 3 energy levels shown here. Okay, right now, well, let me intensify the lamp so you see more photons coming out of the lamp. And what you start to see is that well, this looks kind of messy, but so let me change it to beam mode. Okay, well, the lasing hasn't happened yet, but laser power should increase if I intensify the lamp. Nothing happens. Excuse me. Lasing. Why? I wonder why lasing is occurring. Well, it's happening gradually, but yeah, it started happening. Okay. Now see the strength, the power of the laser is getting stronger to the danger level. So the lasing is happening very intensely inside. See, the standing wave is produced within this chamber. So that's how the form factor of this lasing device is designed. Okay. Well, so we are using this photons coming out of the right window, right mirror. Okay. Well, wavelength of the 633 comes out, nanometers come out. The solid state laser diode, that's the second type of laser device that uses the semiconductor instead of gas, so it's more portable and smaller. You can make a much smaller device and more stable, because you don't have to make a cylindrical chamber, right? It's all solid chip. It's made out of these 2 types of semiconductor, p-doped and n-doped. I think you have seen this somewhere, if you remember. That's the diode, basically. When you learned transistor, you learned you can make 2 types of doped semiconductor, p-type and n-type. And then when you apply the electric voltage across the diode, the laser beam come out of from the interface. They're called the depletion region. But the property of the semiconductor lasers, the power level is low, so it's not can be used for something strong like laser, laser fusion or something like that. So when you run current through the silicon wafer or chip, emits an intense beam of coherent light, and that's used in optical storage, reading and writing the optical storage device. I don't know if you have used CD or DVD, but this is how we used to store data or music, barcode reader or something like that. Yeah, we use those devices. The semiconductor laser. This isn't semiconductor, the gas laser, but this is the most powerful laser at the National Ignition Facility in the States, and it's used for nuclear weapon research. They basically produce nuclear fission or fusion inside this little pellet that has just a 5 mm wide, and then by applying this very intense laser from all directions, we can inertially confine the hydrogen fuse plasma, hydrogen plasma. That that produces this much energy. And that's more than, well, in picosecond, it's more than all of the US electricity use, energy use. So that's extremely powerful lasering device for a defense purpose. But there are many other, peaceful application of lasers, such as laser cutting, for machining or welding. It's also used as a welder, right? Or medical treatment for skin cancer or something like that, or LASIK surgery for eye treatment. Yeah, they use laser beam, and most commonly we use the optical communication nowadays to for the high-speed internet communication, right? I'm using it too. Yes, the Japan has all of them, the communications now optically done. So as a light source they use the laser, right? Because it's intense and it's collimated, so it doesn't attenuate like unlike white light or some incollimated incoherent light. And then we use in a physics experiment as well, because the wavelength is very precise and unique. You can produce a wide variety of wavelengths at the very high precision. And well, this is one of them, called the LIGO device, which last year for the first time they detected the existence of the gravitational waves using this device. It's basically the Michelson-Morley interferometer that in case you wonder what it is, you can look it up. Basically shoot the laser from two perpendicular directions and see at the same time with the and distance is the same, so they should hit at this place at the same time with the same phase, right? In phase, if the distance was same. But in fact, it's not the same because the gravity wave is traveling through this facility. So the length of this side 6 and this side 5 is slightly different. It varies a little bit different because of the gravitational wave coming from maybe like a merging black hole or supermassive black hole or supernova or something like that, some massive event happening in the universe. And then lastly, well, this is kind of cute usage for the laser, but you could, I mean, I don't know if you have the laser pen, but you can use it to play cats love them. The laser pointer chasing after. They don't know what it is, but yeah. So that's it for today, and see you. Well, stay safe and see you Friday. Thank you.